Hello everyone, welcome back. So let us continue our discussion. We are in week 8 and this is our lecture 3. So let us continue our discussion on shear stress distribution, right? Now if you recall previous discussion, we have derived an expression tau is equal to VQ by IB. And we also solve examples like if you have a rectangular cross section and if you have I sections, these are the problems we have already solved, right? So if you have I section and rectangular cross section, these are done. Now the question is, if you have a unsymmetric section and then how to derive the expressions for tau and what is the impact of tau in that case if you have an unsymmetric section. So for that, let us first take the bending problem, because if the section is not symmetric, then first we have to figure out the bending stress distribution and then we will come to the shear stress distribution. So let us consider a beam again. So this is a simply supported beam and at the ends we apply sagging moment. Right. So we have the moment, say this is our x direction and this is z direction. So we apply moment mz. Now we have already derived the expression sigma by y is equal to m by I is equal to E by R, right? Now we have a section which is not symmetric. So let this be y and this is z and x is perpendicular to the page, and then we have a asymmetric section. Say this is the section, any arbitrary section. Now obviously even for an arbitrary section, we will have a centroidal axis, and let this centroidal axis be BB. Okay. And the angle this centroidal axis makes with y-axis is beta. And what we do, we consider differential element. So the area of this is dA and the distance of this, it's CG from this BB, that is centroidal axis or neutral axis, let this be y prime. Okay. Now because of this bending, which is about z axis, what we have, epsilon x is equal to k times y prime right? This we have already earlier developed this model. So sigma x is equal to k times E times y prime. Now if you consider the force acting over this area dA, obviously this is the multiplication of the stress which is acting over a area dA, right? So then what we get is instead of sigma x, we can write k times E times y prime and then dA. So effectively the force, what we get is some k prime y prime times dA, right? Okay. Now also note that sigma y and sigma z is equal to 0 because there is only bending mz is applied, and this mz, which is actually causing a sagging deformation here, it will contribute to develop sigma x, that is the stress in the axial direction, right? Now we can also calculate what is Fx, that is the total force, which is k prime y prime dA. So this dA is equal to, say, dy and dz, right? So it will be double integral because we have area and that's the total force, and to maintain equilibrium this has to be equal to 0, right? If you recall, for a rectangular section we developed bending stress model, and above neutral axis you may have tension, below then compression, or vice versa. For example, in this case it is a sagging profile, so we have tension at the bottom, compression at the top, so we can quantify the compressive force and tensile force, and they too should balance each other so that net force is 0, right? Now what it indicates? It indicates that double integral y prime dA is equal to 0, right? And that actually defines the neutral axis or centroidal axis BB. And this is nothing but the first moment of area about the centroidal axis, right? Okay. So now let us consider moment about y-axis. So moment about y-axis is what? We have sigma x dA, that is the force, then times z, and double integral is the moment about y-axis, which is nothing but k prime double integral y prime dA times z, right? Now we can also find out moment about z-axis, and you can show that this moment is k prime double integral, then we have y prime, then y dA, and this is nothing but minus of mz, because they too should balance each other, right? Okay. Now, let us just redraw this and see the expression of y prime, right? Our objective is to express y prime in terms of the known coordinates y and z. Let us see how we can do that. For that, what we do is redraw this section. So we have y and z axis, and the differential area is somewhere here. Also we have neutral axis, so this is the neutral axis and it makes an angle beta. So what we do, we drop the perpendicular over the neutral axis, and that is y prime. Now we also draw the perpendicular over z axis and then extend this where this line says CB, it is parallel to neutral axis, and so this point is A and this point is D. Our objective is to find out y prime. Now y prime, you see from geometry what we get, AC minus CD. Now AC we have to quantify, so for that let us just draw another perpendicular here, and this angle is 90 degree minus beta. Now let this origin be O, so OB is Z, that is the Z coordinate here, so it has a coordinate of Y, Z, and EB, so this point is E, EB is equal to OB sine of 90 degree minus beta. Therefore, it is OB cos of beta. OB is Z, so effectively EB is Z cos of beta. So CD is equal to Z cos of beta, because CD is equal to EB. Then we can now express y prime, which is AC minus CD. So we have y sine of beta minus Z cos of beta. So we get the expression of y prime in terms of yz and the orientation of the neutral axis, which is at an angle beta with the vertical axis, right? Okay. Now what we are going to do is we substitute this expression of y into the expression here. So recall the first expression we derived for moment about y-axis, right? So moment about y-axis was double integral sigma x z times dA. And this is equal to double integral k prime y prime z dA, which is equal to 0 because there is no moment, right? So what we get, double integral k prime, in place of y prime we have y sine beta minus z cos of beta times z dA, which is equal to 0. Then if we open the bracket, what we have is double integral k prime yz sine of beta minus z square cos of beta times dA, which is equal to 0. So what we get? We get double integral yz dA sine of beta is equal to double integral z square dA cos of beta. This is a very important expression because what next we get is tan beta. So effectively we get tan beta equal to double integral z square dA divided by double integral yz dA. So we can identify these integrals. So the first one in the numerator is nothing but iy, and the expression in the denominator is iyz. This is a very important expression because from this expression we get beta equal to tan inverse of this quantity, and that gives us the orientation of the neutral axis. So this is important because beta equal to tan inverse iy by iyz, and it gives the orientation of the neutral axis with respect to y. Now if we have any arbitrary section, we can first find out iy and iyz, and the moment we do that, we get the orientation of the neutral axis. Now next task is to find out the moment about z axis, and in that expression again we'll put the expression of y prime and we'll see what we get. So tan beta is equal to iy divided by I. Now let us consider the second equation. We had k prime double integral y prime then y dA is equal to minus mz, right? That was the second equation, and in this equation let us put k prime and double integral. In place of y prime we have y sine of beta minus z cos of beta times y dA is equal to minus of. Now again we can open the bracket, so we have k prime then double integral y square dA sine of beta minus double integral yz dA cos of beta is equal to minus mz. So effectively what we have, k prime is equal to mz divided by the first expression. We can identify it is iz sine of beta minus yz cos of beta. And we can take this negative sign inside. So effectively we'll have this one positive and this is negative. So we have the expression of k prime, and then we can use this expression to find out the bending stress, right? So sigma x is equal to k prime times y prime that we derived at the very beginning. Now in place of k prime, we can put the expression that we have just derived, and we also know the expression of y prime. So now we have the bending stress for any asymmetric section. So effectively we have mz, in place of y prime, we have y sine of beta minus z cos of beta divided by I of yz cos of beta minus iz sine of beta. And that is the expression of sigma x. Now you see, we can select any point in yz coordinate system. So effectively we know the coordinate y and z, and then for any point above or below neutral axis, we can use this expression to find out the bending stress for this section which is not symmetric and regular, right? For any section now, we can first find out Ixx or Iyy, Izz and Iyz. Then once we know Iyy, Iyz, using this expression we can find out the orientation of the neutral axis, and then using the second expression sigma x, we can find out the bending stress distribution over the complete section. Now we can actually modify this expression, because you see we have sine and cosine in numerator and denominator. So what we can do, we can write down this expression as y of tan beta minus z divided by Iyz minus Iz times tan beta, and we have mz here. Now we know the expression of tan beta, and if we put the expression, we get the final expression of sigma x in a very compact form. So we have y times tan beta. In place of tan beta, we can write down Iy by Iyz. So we'll have Iy here minus z times Iyz divided by Iyz square minus Iy Iz times mz. That's the final expression we get for sigma x. Now if you look at this expression, again it's a linear variation, because we have y to the power 1 and z to the power 1. So as we move away from the neutral axis, we find out this y and z for that particular point. Say for example, if we take this point, we know the coordinate of this point. The moment we identify the coordinate of the point from this expression, we can find out what is sigma x. Similarly, if we take this point, we know the coordinate of this point, and we can find out what is the value of sigma x here. And depending upon the sign, we can identify whether it is tensile or compressive. Just like we did for a rectangular section. For a rectangular section, we have neutral axis at the middle, And then for that, we easily draw the linear variation and we identify, depending upon the type of the bending moment, whether we have compression at the top or tension at the top, right? Okay. Now, if we consider special case where we have IYZ is equal to 0. That means the section has at least one axis of symmetry, and if you have that, then what we get, y times Iy, second term will be 0. So this is the special case, z times Iyz, because we have Iyz equal to 0, so second term is not there. Similarly, in the denominator, first term is not there, so we have Iy times Iz, and there is a minus, you have z here, so effectively you get My by Iz. Again, the same expression that we derived earlier for rectangular cross section, or actually regular cross sections where we have axis of symmetry, right? So effectively we have to remember this expression of sigma x and tan beta. If we recall these two expressions for any arbitrary section, we can now plot the bending stress distribution. So our main objective is to find out the bending stress. For that, this expression and this expression, these two are extremely important. Using these two, we can plot the bending stress distribution. Now, with that background, let us move forward and let us see how we can now figure out the shear stress distribution for a section other than rectangular or I sections that we have already considered, right? Now, for that again, let us consider a beam. And let us consider two sections which are at a distance dx. And at these two sections, let us apply hogging bending moment. And if you recall, what we did, we considered, say, m, and then over dx it varies m plus dm. Then using this information, we identified the unbalanced force, right? And then from that unbalanced force, we identified the amount of shear we need at a particular section. Now here, say the section is a channel so the thickness is T, and let us for the time being consider the thickness of the wave also T. This is B, and the depth is D. Now, if we just draw a different view, because we have to identify the unbalanced force, and that unbalanced force we will quantify and identify the direction of the shear. So for that, let us consider the channel section in (3D) view, right? Okay. Obviously, at this section, we have applied the bending moment, which is m plus dm. And at this section, at the left end, we apply m. So this is the thickness t, and let us consider a small strip. Now this distance is z. Now we have applied a hogging moment. That means at the top we'll have tension and at the bottom we'll have compression. And at this phase we'll have sigma x plus, sigma x due to the bending moment, m plus dm. At this end, we'll have sigma x due to mx or m. Okay. Now, obviously, the magnitude of the moment here is more than what we have on the other side. Therefore, the value of stress here on the right hand side will be more, right? Let this be sigma x1, or let this be sigma x2, and this is x1. So sigma x1 is equal to m by I times d by 2. And if we multiply both sides with the cross-sectional area is T times Z, then effectively we get the force, say P1 is equal to sigma x1 times T times Z. So what we have is m by I times d by 2 times T times Z. Similarly, we have P2 is equal to m plus dm divided by I times d by 2 times Tz. So we have quantified the forces acting at the two ends. Now P2 minus P1 is the unbalanced force, and this is equal to dm by I times d by 2 times Pz. Now obviously on the right hand side we have more force here. That means this small section will start sliding on the right hand side, and someone should prevent it, and that comes from the shear. So to prevent the shear, it should act. Let me just erase these lines. So it should act along this direction. Therefore, on this face we have shear going this way, and on the opposite face it will come this way. Right? Okay. Now, this is the shear that is causing a shear force which is acting over an area of thickness T and length dx. So we can quantify that shear force. So the shear force is equal to tau times dx, the length of this segment is dx, times the thickness of the section d. Obviously, these two should balance each other, so we get tau dx times t is equal to dm by I times d by 2 t times z. So the t gets cancelled. So what we have, tau is equal to dm dx times 1 by I times d by 2 times. Recall, we earlier derived dm dx is equal to v. That is the shear force acting at that particular section. So therefore we get tau is equal to v times 1 by I times d by 2 times z. So we have v z d divided by twice I. So that's the shear stress acting over this cross section. Now, if I complete this diagram for the entire section, so the shear flow will be like this. Obviously, in the bottom flange, it will be in the reverse direction and it will close the path. So that's how the shear flow will occur in this section. So if you draw the section, now we have a channel Now for this channel, we have the shear flow diagram. For the applied moment, which is hogging, right? Okay. Now, what you can see is the nature of the shear stress distribution. We'll plot the shear stress diagram across the section in a minute. But the point to be noted here, you can see we applied a hogging moment that was causing bending, but because we have a section which is not symmetric about y-axis, now obviously these two stresses in the flange, they are equal in magnitude and opposite in direction and separated by a lever arm. Obviously, that will cause a rotation, right? That means for this type of section, if we apply, say, bending, that will cause a rotation at the section level. Now, we applied hogging moment. That means at this fiber, it was tensile. So here we had tensile stress and here we have compressive stress. If we apply sagging bending moment, obviously this nature will reverse and we'll have tensile at the bottom. Okay. Now we have already quantified the expression of the shear stress. Now at Z, recall Z is the distance of that section we considered from the extreme end, right? Now at this point, Z is 0. So here Z is 0. If Z is 0, obviously tau is also 0. So if we draw the shear stress distribution, it starts from 0, and as we progress and we reach up to the center line of the wave, so this distance is B. So at this point, we have Z equal to B, and this is now VBD divided by twice I, and there is a linear variation. So we get the shear stress distribution in flange. It will be same for the bottom flange. So we have 0, and then this is VBD divided by twice I. Now for the wave, we can draw the shear force distribution. So it will be for the wave, tau is equal to VQ by IB, and we already know this is a quadratic variation. So effectively it will be like this. Okay. Now just imagine we apply a force vertically downward, say at this point. Now obviously, if the force is applied here, it has a eccentricity with the vertical axis of the wave. So this is the eccentricity, and we apply a force P. Then if we consider the moments about the point, so this is the point O, and then apply moment equilibrium, and let us see what we have. So P times E is the moment caused by this force, and obviously P is nothing but our shear force V. We'll put that in a minute. And then this is equal to, we have the shear force acting in the flange. So for that, we can find out the area under this triangle. So that is half times V times BD divided by twice I times B times T is the total shear force. Now that multiplied by the lever arm between them is basically the couple developed. So this is the D, which will be balanced by this arrangement. Now then what we get, this P equal to V. So on the left hand side, we can now put V. So what we have, E is equal to half B square D square divided by Y side. And there is a T here. So we can write this as B square D square T divided by 4I. So that's the expression of the eccentricity. What is the meaning of it? The meaning is, if the shear force is applied at this point, which is at a distance E from the center line of the wave, then that will cause a rotation which will counterbalance the rotation caused by the shear stresses in the two flanges, right? One at the top, another at the bottom. Otherwise, for these type of sections, what will happen if we apply a bending, that will also cause a rotation at the section level. Now this point, which is at a distance E, this is called shear center. So shear center. So for the channel section, the shear center is at a distance E from the center line of the wave and over the axis of symmetry, as you can see here. And if the shear force passes through that point, then it will automatically counterbalance the couple developed by the shear flow, which is in the two flanges, one at the top, another at the bottom, right? This is very important. So when we design a section, we have to be careful for asymmetric sections, because the shear force must pass through the shear center, and if it passes through the shear center, then that will not cause any rotation at the section level. Otherwise, even the bending will cause a rotation because of the asymmetry at the section level we have. Right. So what we have defined is shear center for a asymmetric section. So with that, let us close here. We'll continue on this topic and we will evaluate shear center for asymmetric section further in the next class. Thank you very much.